Easter Island's collapse story has been repeated in best-selling books for 2 decades, treated as settled fact. No one had ever measured the island's ancient farmland precisely enough to test it. A team of Earth scientists pointed machine learning at satellite soil data. Anyway, expecting to confirm what everyone already believed. The numbers that came back didn't match the story at all. The story everyone thought was settled. Rapa Nui, known to most of the world as Easter Island, sits more than 2,000 kilometers from the nearest inhabited island and roughly 3,700 kilometers from South America, making it one of the most remote places human beings have ever permanently settled. It's nearly 1,000 Moai statues, ranging from about 2 to 20 meters tall and carved from volcanic rock between roughly the 10th and 16th centuries, have puzzled outsiders since European sailors first spotted them in 1722, wondering how such a small, isolated population managed to carve and move such enormous stone figures. Geographer Jared Diamond's 2005 book, Collapse, turned Rapa Nui into arguably the most cited real-world example of ecological self-destruction in modern popular science writing. Diamond's version of events described a population that grew rapidly, stripped the island of its trees and resources, competing to build ever bigger statues, and then crashed catastrophically before Europeans ever set foot on the island, leaving behind the mysterious stone giants as a warning about the dangers of unchecked resource use. That story spread far beyond academic circles, showing up in classrooms, documentaries, and casual conversation as a kind of morality tale about civilizational collapse. Other researchers had pushed back against that version of events for years, arguing the archaeological evidence never fully supported such a dramatic crash. Settling that argument required better data than anyone had previously managed to collect, and getting that data meant turning to tools nobody studying Rapa Nui had access to even a decade earlier. Why scientists needed a new tool. Understanding how many people Rapa Nui could ever realistically supported required knowing how much of the island had actually been farmed, specifically through a distinctive technique called rock gardening, where islanders broke volcanic rock into small pieces and mixed it directly into the soil. This method, also used historically by the Maori in New Zealand and by indigenous farmers in the American Southwest, exposes more mineral surface area, helping poor volcanic soil release nutrients more effectively for crops like sweet potato, taro, and yams. Lipo has pointed out that modern agriculture achieves the same basic effect, using machines to crush rock, while the ancient Rapa Nui accomplished it entirely by hand, breaking stone piece by piece and working it into the ground. Earlier researchers had tried estimating how much of the island was covered by these rock gardens, using older satellite imagery, and their estimates varied wildly, ranging anywhere from about 1.6 to 8.1 square miles, depending on the study. A significant part of that inconsistency came down to a basic technical problem, since older imaging methods frequently misidentified other features, including roads and natural rocky terrain, as farmed rock gardens, inflating the apparent scale of ancient agriculture considerably. Early European visitors to the island had themselves estimated that rock gardens covered roughly 10% of the island's entire land area, a figure that later satellite studies never managed to fully confirm or properly reconcile with more careful ground-level observation. That level of uncertainty made it essentially impossible to calculate a reliable historical population estimate, since food production capacity is one of the most direct ways archaeologists can estimate how many people a resource-limited island like this could have ever actually sustained. Solving that measurement problem meant researchers needed a tool capable of telling the difference between an actual rock garden and an ordinary rocky hillside with far more precision than a human eye scanning a satellite photo could reliably manage. Teaching a computer to spot a rock garden. In 2024, a research team led by Dylan Davis, a postdoctoral researcher at Columbia University's Lamont Doherty Earth Observatory, working alongside Robert DiNapoli, Gina Paccarati, Terry Hunt, and Carl Lipo, published a study in the journal Science Advances, built around exactly this problem. The team first conducted ground surveys across Rapa Nui in 1919 and 2023, physically measuring the chemical and geological signatures of confirmed rock gardens compared against bare soil, grassland, forest, and other terrain, types found across the island. Using that carefully verified ground truth data, the researchers trained 3 separate machine learning models to recognize rock gardens automatically within high-resolution satellite imagery, drawing specifically on shortwave infrared and near-infrared data. Davis explained that this particular kind of imaging works well for this task because it picks up on subtle differences in moisture content and mineral composition, invisible to an ordinary camera. Exactly the kind of signature a rock garden's disturbed, mixed soil produces, compared to untouched natural ground nearby. Once trained, the models scanned the entire island using this method, and the research team manually verified the results, finding the model correctly identified rock gardens with roughly 83% accuracy. That level of accuracy, openly reported rather than exaggerated, let the researchers calculate an island-wide rock garden estimate considerably more precise than anything earlier satellite-based studies had managed to produce, using less specialized imaging methods. Robert DiNapoli, one of the study's co-authors, noted that sweet potatoes, grown in numerous ancient varieties, served as the primary mainstay crop, supported by this specific farming method, supplemented by smaller amounts of dry land, taro, yams, and bananas. The number that challenged the collapse story. The machine learning model's results dramatically shrank the previous estimates for how much of Rapa Nui had ever been covered in rock gardens. From a range of 1.6 to 8.1 square miles, down to just about 0.29 square miles, an area covering roughly 3/4 of a single square kilometer. That number mattered enormously, since rock gardening supplied nearly half of the nutrition ancient Rapa Nui people depended on for survival, according to the researchers' broader food system analysis. Combining that smaller, more accurate rock garden estimate with calculations for fishing and other marine food sources, the team calculated that Rapa Nui could have sustainably supported a maximum population of around 3,901 people, give or take roughly 800 individuals. That figure lines up closely with written accounts from early European visitors to the island, who estimated a population of somewhere between 3,000 and 4,000 people at the time of first contact, considerably smaller than the dramatically larger population some collapse-focused theories had assumed existed before any supposed catastrophic crash. Lipo summarized the team's conclusion plainly, stating that the island's ecological limits meant it likely could never have supported a large population capable of the kind of rapid boom and catastrophic bust central to the popular collapse narrative. Instead of a society that grew too large and then destroyed itself, the machine learning-powered evidence pointed toward a small, resilient population that had adapted successfully to one of the most resource-limited environments on the entire planet. If you're enjoying this deep dive, hitting subscribe means you won't miss the next one. That finding directly contradicted decades of popular science writing built around Rapa Nui as a warning story, and not every researcher in the field was ready to accept it without pushing back hard. Not everyone is convinced. Joanne Van Tilburg, an archaeologist at UCLA and director of the long-running Easter Island Statue Project, publicly challenged the 2024 findings, telling reporters the new study's conclusions ran contrary to nearly all prior archaeological literature on the subject. Van Tilburg argued that basing a population estimate primarily on one single type of evidence, rock gardening alone, risked oversimplifying the far more complex variation in soil fertility and food sources found across different parts of the island, and that the framing of a low but sustainable population amounted to an overreach given the data actually available. Davis and his colleagues acknowledged directly that a fully comprehensive study of Rapa Nui's historical population has never actually been completed, and that their own estimate, while grounded in verified machine learning results, still represents one particular calculation built from one particular category of evidence, rather than a final, universally accepted number. The researchers stood by their estimate as a solid, defensible calculation, while remaining open to future refinement as more data eventually becomes available. Noting the current figure aligns well with independent early European written accounts, even if it does not resolve every open question about the island's food systems. That kind of open, unresolved scientific disagreement, real named researchers publicly challenging each other's interpretation of the same underlying data, is exactly the sign of a genuinely active, evolving area of research rather than a single settled headline. It also set the stage for an entirely separate AI-assisted project the following year, one that would end up challenging a completely different assumption about how Rapa Nui's most famous monuments actually got built in the first place. A second AI project asks who actually carved the statues. In October 2023, a wildfire swept across the Rano Raraku quarry, the volcanic crater where the overwhelming majority of Rapa Nui's Moai statues were originally carved directly out of the rock face. That fire burned several statues badly enough to leave them permanently disfigured, adding fresh urgency to a site already showing signs of vulnerability. Concerned that the fire damage might worsen, or that another disaster could permanently destroy irreplaceable archaeological detail. A community group on the island reached out to researchers in January 2024, asking whether the quarry could be thoroughly documented in case anything happened to it in the future. Carl Lipo, an anthropology professor at Binghamton University, along with Terry Hunt from the University of Arizona, Gina Pacarati of Hangaroa on Rapa Nui, Thomas Pingle, Kevin Hurd, and several additional collaborators took on that documentation project directly. The team conducted around 30 separate drone flights over the quarry, capturing roughly 22,000 individual photographs at close, 30-meter increments. An enormous volume of visual data that would have been essentially impossible to collect and analyze using older manual survey methods within any reasonable time frame, using a computational technique called structure from motion photogrammetry, which stitches together large numbers of overlapping photographs into a single, unified, three-dimensional model. The team eventually processed 11,686 of those drone images into what became the first ever high-resolution, three-dimensional digital model of the entire Rano-Raraku quarry. That painstaking computational process took several months to complete, and the results ended up published in the journal PLOS 1 on November 26, 2025, revealing details about statue production nobody had ever been able to properly document before. What the 3D model actually revealed. Lipo described the resulting quarry model as something like an archaeological Disneyland, giving researchers the ability to examine tops, sides, and hard-to-reach areas of the carving sites that would be genuinely impossible to properly access or photograph on foot. Christopher Stevenson, an archaeologist at Virginia Commonwealth University, who was not involved in the study, independently praised the research team's approach as genuinely innovative once the results became public. The comprehensive digital documentation revealed a complex spatial organization of production activity spread across multiple separate workshop areas throughout the quarry, rather than one single, centrally coordinated operation. Based on this detailed spatial mapping, the research team concluded that the MOI were most likely produced by numerous small, independent groups working somewhat separately from each other, likely representing individual family clans of roughly 15 to 25 people each, rather than a single centralized management system directing all statue production across the island from one unified authority. That conclusion challenges an assumption that had lingered in popular imagination for years: the idea of a rigid, centrally controlled labor system, possibly even involving forced or slave labor, responsible for producing hundreds of multi-ton stone statues under some kind of singular ruling authority. Instead, the drone-based evidence points toward a more decentralized, community-driven production model, with separate family groups, each responsible for their own carving work within the shared quarry space. A picture of cooperative but independent labor, rather than top-down control. That shift in understanding how the statues got made connects directly to an entirely separate, decades-old mystery about exactly how these finished multi-ton statues ever moved from the quarry to their final resting places scattered across the island. The old mystery of how the statues moved, moving a Moai statue weighing several tons across miles of uneven terrain, with no wheels, no draft animals, and no modern machinery, has puzzled researchers for generations, producing a wide range of competing theories over the decades. Some researchers proposed the statues were dragged horizontally on wooden sleds or rolled along log tracks, methods requiring enormous amounts of timber and manpower working together simultaneously, an assumption that fit neatly alongside the older collapse narrative, since a deforestation-heavy transport method would have directly contributed to stripping the island bare of trees. A very different theory, sometimes called the walking hypothesis, proposed instead that the statues were transported upright, tilted slightly forward, and rocked side to side, using ropes pulled by teams of people. A motion that makes the statue appear to walk forward on its own base, rather than being dragged flat along the ground. Lipo and Hunt tested this exact idea directly in a 2012 experiment, using 18 people pulling ropes to successfully walk a 4.35-ton replica Moai a full 100 meters in just 40 minutes, rocking the upright statue forward step by step in a controlled, repeatable motion. That experiment demonstrated the walking method was physically possible, using a reasonably sized team and basic rope technology available to the ancient Rapa Nui, directly challenging older theories that assumed transport required either extensive log roads or a far larger, more centrally organized workforce. Confirming whether real ancient statues actually got moved this way across the island, rather than simply proving the method could theoretically work in a controlled modern test, required going back to the statues themselves and looking for physical evidence matching the walking hypothesis. Specifically, what the newest data says about walking, published in the November 2025 issue of the Journal of Archaeological Science, a follow-up study by Lipo and Hunt surveyed 962 moai across the island, looking for physical clues about how each one was actually transported. They focused closely on 62 statues still sitting along ancient transport roads, since statues abandoned mid-journey offer a rare window into the transport process itself. Those 62 road statues shared a consistent trait: a D-shaped base paired with a forward lean of 6 to 15 degrees, exactly what the walking hypothesis predicts. A statue meant to be rocked upright would need a rounded base to tip side to side and a forward-leaning center of gravity to pitch ahead with each rock. That pattern, found specifically among statues abandoned along transport routes rather than ones already at their final platforms, offers far stronger evidence than the 2012 experiment alone. One successful demonstration shows a method is possible. Finding that exact predicted shape repeated across dozens of real statues suggests the Rapa Nui were designing them to walk from the very start. Why location itself turned out to be a clue. Separate from the specific questions of population size and transport method, researchers working with Geographic Information System technology, commonly called GIS, mapped the precise locations and physical orientations of more than 1,000 moai statues across the entire island, uncovering patterns invisible to anyone simply walking the terrain and observing statues one at a time. This kind of large-scale spatial mapping revealed that statue placement was far from random, with many moai clustering specifically near sources of fresh water, a genuinely scarce and valuable resource on an island with limited natural springs and streams. That water-related clustering pattern suggests the statues likely served a dual purpose beyond pure ceremonial symbolism, potentially marking locations that were simultaneously spiritually significant and practically essential for basic survival. Researchers have also documented that many moai face inward toward inhabited areas of the island, rather than outward toward the ocean, reinforcing the widely accepted interpretation that these statues represented watchful ancestors looking after their living descendants, rather than sentries guarding against threats arriving by sea. Remote sensing technology used for this kind of mapping work has evolved dramatically over the past few decades, starting with early kite-mounted cameras equipped with mechanical shutters back in 2001 and progressing to modern drones now capable of processing 20,000 photographs within just a few hours of flight time. Rapa Nui's largely treeless landscape makes it particularly well suited to this kind of aerial analysis, since almost nothing blocks a clear overhead view of the terrain, letting researchers build genuinely comprehensive spatial datasets that would have taken years of manual fieldwork to assemble using older methods alone. A new kind of digital model is racing against the ocean itself. While one set of researchers used computational tools to study how the Moai were built and moved, a completely separate team has been using similarly advanced digital modeling to figure out how much longer some of these statues actually have left standing in their original locations at all. Most Moai and their ceremonial Ahu platforms, dating to roughly 1250 to 1500 AD, sit directly along Rapa Nui's coastline, placing them squarely in the path of a threat nobody who originally built them could have ever anticipated: modern sea level rise, driven by global climate change. In August 2025, a research team led by Noah Pawa, a doctoral student in the Department of Earth Sciences at the University of Hawaii at Manoa, working alongside Dean Chip Fletcher, published a study in the Journal of Cultural Heritage, building a detailed digital twin of the coastline surrounding Ahu Tongariki, the island's most famous and largest ceremonial platform. The team used advanced computer modeling to simulate future wave behavior along the coast, then mapped exactly where projected flooding would reach under various sea level rise scenarios, overlaying those flood projections directly onto the known locations of cultural and archaeological assets provided by local Rapa Nui partners. The resulting model projected that by 2080, rising seas could allow seasonal storm waves to reach Ahu Tongariki itself, a platform currently home to 15 standing Moai and considered one of the most iconic archaeological sites on the entire island. The same flooding risk extends to at least 51 separate cultural assets scattered along the coastline, according to the study's findings. Pawa explained that the goal behind building this kind of detailed digital simulation was to give island officials and heritage managers a genuine head start, allowing proactive planning and protective measures rather than reacting only after irreversible damage had already occurred. Why this threat is already visible today. This is not a distant, theoretical concern confined to computer models. A 10-foot stone wall at the Ura Uranga Te Mahina site on Rapa Nui's southern coast has already collapsed from wave damage, according to the University of the Highlands and Islands Archaeology Institute. Separately, the 2022 wildfire at the Rano Raraku quarry burned several statues badly enough to leave permanent damage, a reminder that fire threatens these monuments just as much as water. Rainfall has also declined, dropping to 992 millimeters in 2020 from 1,311 in 1991, adding water scarcity to the island's roughly 8,000 residents on top of coastal flooding risk. A United Nations report on climate threats to World Heritage sites flagged Rapa Nui directly, warning that wave energy hitting the IHU platform's basalt walls could eventually topple some Moai from their bases. Some protection has already started. A seawall now shields Moai at Ahu Runga Vai, and reforestation using erosion-resistant ironwood trees is underway elsewhere, though researchers caution the trees will take years to offer real protection. Proposed larger defenses range from breakwaters to relocating monuments entirely, an option complicated by the statue's role as burial markers tied to specific ancestors. What AI can and cannot actually tell us. Every one of the specific projects described throughout this video relied on machine learning or computational modeling for a fairly specific, well-defined task: distinguishing a rock garden from bare soil in satellite imagery, stitching together tens of thousands of individual photographs into one unified three-dimensional model, or simulating future wave behavior along a specific stretch of coastline. None of these tools independently decided what the underlying patterns actually meant, historically or culturally. That interpretive work remained squarely in the hands of the named human archaeologists, earth scientists, and local Rapa Nui community partners involved in each individual study. Researchers working in this specific field have also been openly candid about real, documented limitations affecting this kind of remote sensing and modeling work. Earlier satellite-based rock garden studies had genuinely misidentified ordinary roads as farmed agricultural land, before more carefully trained models corrected that specific error. A reminder that even sophisticated computational tools require careful validation against real, physically verified ground truth data before their results can be fully trusted. Van Tilburg's public pushback against the 2024 population study reinforces this same broader point directly, since even a well-built, carefully validated machine learning model still only measures one specific category of evidence, leaving plenty of room for legitimate scientific disagreement about what that evidence ultimately proves about the island's full history. That honest, transparent handling of both capability and limitation is exactly what separates this real, peer-reviewed research from an exaggerated viral headline promising a single AI model finally solved an ancient mystery completely on its own. Every study described here still required years of prior ground survey work, careful manual verification, and ongoing public debate among named specialists working in the field. Exactly the kind of grounded, incremental scientific progress that tends to get lost whenever a flashy headline reaches for the word shocking instead of the far more accurate word contested. The speculative question still left open. None of this means every question about Rapa Nui's history is now settled. Van Tilburg's critique of the population study remains unresolved, and researchers themselves admit a truly comprehensive study has never been completed using every category of evidence at once. Future models trained on richer ground survey data could push that 3,901 figure higher or lower. The quarry study raises its own new questions too. If independent family clans really did carve the Moai separately, how did any broader island-wide authority coordinate resources or belief across those groups? Something drone footage alone cannot answer. And PAUA's climate modeling raises an entirely different kind of question: whether digital forecasting can actually translate into funded protection before rising seas make the debate purely academic. Whether future research ever combines all three threads into one clearer picture remains genuinely open. That layered uncertainty, real progress, paired with real unanswered questions, is what an honest, ongoing mystery actually looks like. Far more interesting than any headline claiming it's all been solved. Verdict. Here is where things actually stand. In 2024, a team led by Dylan Davis at Columbia University trained machine learning models on satellite imagery to map rock gardens across Rapa Nui with 83% accuracy, shrinking previous farmland estimates and calculating a maximum sustainable population of around 3,901 people, directly challenging the ecological collapse, story made famous by Jared Diamond's book, Collapse. though archaeologist Jo Ann van Tilburg has publicly called the conclusion an overreach. In 2025, Carl Lipo and Terry Hunt used drone photogrammetry to build the first high-resolution 3D model of the Rano Raraku quarry from nearly 12,000 photographs, revealing that small family clans of 15 to 25 people likely carved the statues rather than one centralized labor system. A follow-up study that same year, surveying 962 moai, found physical evidence supporting the theory that the statues were walked upright to their final locations rather than dragged. Separately, a University of Hawaii team, led by Noah Paua, built a digital model of the coastline showing rising seas could flood Ahu Tongariki and at least 51 other cultural sites by 2080. None of this involved a chatbot guessing at old photographs. It involved years of ground survey work, openly reported accuracy rates, named researchers publicly disagreeing with each other, and tools built for a specific, verifiable task. Real progress on an ancient mystery, genuinely surprising in places, still contested in others. If mysteries like this one interest you, subscribing helps more stories like it find their way to you the moment they come out.